Welcome everybody to this seminar. Amir Yehudayoff from the Technion will tell us about new isoperimetric inequalities for convex bodies. Go.
Hi everyone. I'm very happy to be here. I didn't visit Princeton for a very long time. So it feels nice in some sense. I want to talk about Euclidean geometry, which is a very old topic. And I want to tell you some ideas that are new. And all of this is a part of a very long conversation with Emmanuel Millman. And I planned the talk to be very high level. I didn't plan to give very technical parts, and I will try to sort of sketch the main ideas. But please ask me a lot of questions. I don't mind talking about whatever you find interesting. So the very high level question or thing we wanted to understand, or that is in this context, is first isoperimetric questions, which is about the minimum surface area of some body in some geometry when the volume is fixed. So this is one type of question that is related to this talk. Another type of question is if we have a body in high dimension and we see some of its projections to lower dimensions, we see some data of this sort, what can we say about the body? So this is a different type of question that is also related to what I'm going to talk about. And the third type of question is if there is we have some body in some, let's say, Euclidean space, but you can think about it more abstractly, then you can position the body in many ways in the space. You can rotate it, for example, and in our mind, at least, it doesn't really change the body, just some, it's the same body. So how can such symmetries help us to get better bounds, better control? This is the third type of question behind this, the thing I'm going to explain. Okay, so there are three questions, they are related. And I'm going to start by telling you three stories. And each story will demonstrate a specific theorem and some new conclusion. Very, very simple. And the first story is the Lumi-Whitney inequality, which relates, so there is some compact set in Rn. There is a picture here. The picture is in R3, and it's actually not a compact set, but a discrete set, but it demonstrates the same phenomenon. So the statement is that so we can project the body in n ways to the n central hyperplanes that are perpendicular to the standard basis. And the statement is that if all these projections are small, then the volume of the body is not large. And this is a specific statement of this sort. So if we know that all the projections are small, then the body is also small. And this inequality is an equality if the body is a box, like something like this. This is the Cartesian product of three sets. So this is the Loomis-Whitney inequality, and there are many generalizations of it using information.
Before generalizations, Amir, just a simplification. Everybody knows that set in the plane, the area is at most the volume of its projections on the X and Y basis. So that's the simplest Loomis-Whitney inequality when n equals 2.
Yes.
Yeah, so these are, yeah, okay. Now you can, this is a generalization, and now you generalize it more.
There is even a simpler one in dimension 1.
Yes. And actually, the statement you say in the plane can be generalized in two ways. You can either project to the 3 one-dimensional spaces and get a weaker statement than this statement. So, okay, so this is the Loomis-Whitney inequality. I think everybody knows it, but I'm not sure. And maybe many people maybe in combinatorics, it is known as Shearer's inequality. Shearer's inequality is actually a stronger statement, but not on Euclidean space, but on a discrete set. But it's not hard to prove that it's stronger. And it was studied by many people. Ballister and Bolobast extended this somehow. So this is the starting point of this first story. This is this inequality. And now, what is one problem? So I write this inequality in a somewhat disturbing way, but let's write it like this. Okay, so it's the same inequality, just it will be easier to work with. So I just divided and took the log. So I call this number the Loomis-Whitney number of the body K, okay, just a notation. Now, what is the one problem with this inequality is that when we look at it, we need to choose a basis to the space. This inequality, you can sort of implement it only after you chose a basis, which is somewhat not nice, because we want the property of the body and not of the actual coordinate system that we chose. So you can actually have a list of inequalities for any coordinate system, for any orthogonal matrix U. You get also some inequality, the same inequality after you rotated the body in this coordinate system. Okay, so now we have many inequalities for a single body, and with this idea, it is very natural to ask what happens if we choose this rotation at random. So instead of having many inequalities, we sort of combine all of them to one average inequality. So this inequality is true because every single U is non-negative, this number, but maybe now this quantity is actually much larger. So in every single point it is non-negative, but maybe the expectation, it is much larger. And this will give us more information about K. It will be a stronger statement about K, the body K. And so we have this quantity and we can ask, is this inequality sharp? And the answer is no, this inequality is not sharp, and you can actually prove the sharp statement. So this expected value for a convex body is at most the same thing, but when you replace the body with a ball, a Euclidean ball of the same volume. So you can replace K by a ball of the same volume and get a stronger statement. So this number is strictly positive. It's not very difficult to actually compute it, but it's not important for us.
So this
Okay.
The inequality for each particular basis was tight only when it was a box, and so it cannot be a box in all directions.
Yes, exactly. This inequality is sometimes sharp. This number can be 0, but in maybe not 1, but there is some symmetry, but in a very few compared to the whole orthogonal group. So now we see that if we allow rotation, we get stronger information on the body. And this is a nice way to use symmetries. And some comments about just this inequality. So one comment is that this quantity is rotationally invariant. If we have a body and we rotate it, we don't change this measurement, this number, because it goes into the expectation. So this is a nice, this map is symmetric in a way. This is one nice thing. Another thing is that this inequality is an equality just when K is an Euclidean ball. This is the only case of equality for convex sets. And this is another statement. And the third statement, which is maybe most interesting, is that this inequality is strictly stronger than the classical isoperimetric inequality, which says that the body with minimum surface area is a ball. It's not obvious from the way I wrote it, but it is true, and the second story will explain why. Okay.
So you didn't tell us if this theorem is part of the work you are presenting, or this special case was not.
Yes, it is true, and I debated between my 2 ears about this. So I don't think it was known, but it can be proved from known things very easily. So, this specific statement I don't think was written anyway. Okay, so this is the first story. We have Lumi-Whitney inequality. There is a choice of basis which we want to remove from the inequality. We can do an average, and this gives us a stronger statement. So this is story number 1. The second story is a very well-known story. The first statement is a theorem of Cushy, which says the following: you can compute the surface area of a convex body by projections. You choose a random projection onto a hyperplane and measure the expected value. And this expected value is up to some constant equal to the surface area. Okay, so this is Cushy theorem. And again, the constant you can easily compute by plugging a ball. If K is a ball, all of its projections are a ball. So it's very easy to compute the constant if you wish. And this theorem of Cushy relates projections and surface area. This is one of the things, one of the 3 topics I mentioned before. So I also guess all of you know this theorem, but I want to briefly explain a proof or a sketch of the reason why this is true. So this is the theorem. and the sketch is this picture. This picture is all the proof, and now there is a lot of analysis and things like that. But here, let me go over the sketch. The first thing is, if K is not a general convex body, but a polytope, convex polytope, then the surface area is just the sum of the areas of its facets. Just partition the surface to its facets. So this is one statement. A second statement is that once you focus on the projection of a single facet in a random direction, this number is exactly the area of the facet. So if you have a square, it doesn't matter how you put it, the measurement is the same. So this property follows from the maybe uniqueness of the Lebesgue measure, or something like this. Okay, so if you look on a face, which could be, let's say, just a square, then this property holds. If you randomly project the square to a plane, then the expected value of the measurement is the surface area. Okay, so this is the second part in the reasoning. And the third part, which is this picture, is the picture shows a two-dimensional thing. We choose the direction u, and now we fix it. And now we project to the orthogonal complement of u. Then, because the body is convex, above every point in the projection, or
sorry, can I ask a question? In this case, sure. What would Tn prime be?
So I think the easiest thing will be to put here a square.
Uh-huh.
I think this will be the easiest calculation. Sorry, even here, if we put a ball, then the projection of a ball is a ball, and the volume of a ball, we know it.
So it changes based on the shape, I see, okay, yeah.
Yes. Mm-hmm.
Thanks.
Okay, and the third is this picture. The point is that every point in the projection, which is this side, when you see from how many points on the boundary it came from 2 points, exactly 2 points on the boundary. This is true almost surely. So it's not true for this point. For example, here there is 1, but except for a set of measures 0, this is true. So you can measure the projection by summing the projections of all the faces and dividing by 2. So this is the third point. And when you put all of them together, because polytopes are dense in the space of convex sets, you get this. This is a continuous operation. Okay, so this is Cushy's theorem, one way to prove Cushy's theorem. And I really like this picture. I think it demonstrates a lot of something interesting. Okay, now
I think, I don't know what happened before because I don't remember which year it was, but the story of the Buffon needle, of estimating the value of pi by throwing a needle on a floor, you know, which is, let's say, a wooden floor of planks of equal width, and the needle is the size of the width, the probability that it will cross a line. It's basically the same theorem. And then, yeah, it doesn't have to be a needle. Then there is a Buffon noodle theorem, which it can be any piece of spaghetti, still it will be a constant that depends only on the length. And so this theorem is actually true in more generality. I mean, you explained it for convex body, but you can state it for any body. Of course, this thing about the number of times, which happens to be true in a convex body, simplifies the formula here. But it's basically integration along the surface.
Yeah, so you can see if it's not a convex body, there is some multiplicity that is not uniform. It's not always 2. Okay, so now a way to state the isoperimetric inequality, this thing is the surface area up to a constant, the surface area of K. A way to state the isoperimetric inequality is like this. This is the isoperimetric inequality for convex sets. Okay, this is the surface area. This is also the surface area. Okay, now what is the problem here? The problem here, or a problem here, is that this thing is not, so surface area, which is the number written here, is not invariant under volume preserving transformations. So if you sort of change the angles a little bit, but preserve volumes, you can change the surface area significantly. So you can add more symmetries to the thing you have in mind and ask to preserve them as well. So this was so this is the comment. This is not a fine invariant. And then now I think this is true historically. This was what I tried to find out. This is the knowledge I got. But so an observation that Petty was aware of is that if you map a K not to this number, but to 1 over this to the power n, which is a similar thing, but a bit more complicated, then you do get an affine invariant quantity. Okay, so you can replace the measurement that is performed here by a slightly more complicated calculation, and then you get a truly affine invariant quantity. Okay, so this was, I think, known by Petty, known to Petty, I guess.
But is it related to the surface area in any way, this quantity?
It's not related to the surface area. I will comment about this in the next slide. And then Petty said, okay, I know the isoperimetric inequality. Let me prove the corresponding inequality for this quantity. Now, because it went downstairs, the inequality is reversed. But Petty proved this inequality. Okay, so this is a version of the isoperimetric inequality for this quantity, which is affine invariant. Okay, so this is called Petty's inequality. And some remarks about Petty's inequality. So it is affine invariant. This statement is strictly stronger than the isoperimetric inequality because the function 1 over x to the power n is convex. So you just apply, this is Petty's inequality, and this is Jensen's inequality, and you get the isoperimetric inequality. So it is strictly stronger because this inequality is an equality only if all the numbers here are the same. So it actually gives you more information about the equality cases.
If it's not hard to describe, can you like say why it's affine invariant?
I will mention this later.
Okay.
There are two. So Patty's perspective, maybe something like this. This number is the volume of the polar projection body, which is some other body that is related to K. And this allows you to argue this type of, you have a geometric interpretation of this quantity.
I see, thanks. Okay.
And I will mention a little, I will talk a little bit about this later, okay? And the third observation is that you can, what happened? You can replace, this is the nth moment. You can replace it by the 0th moment. The 0th moment is log. And if you do this with log, you get this averaged Loomis-Whitney inequality, which I stated in story number 1. Okay, and so this is the third point about this story, story number 2. Okay. Story number 3 is slightly more abstract, maybe. And maybe some of you actually find this more interesting, I'm not sure. So the story is like this. It starts with an amazing statement that Steiner proved. I think he was the first to do this. So what is written here? We have the convex body, and now we add to it as a Minkowski sum, some multiple of a ball, of a unit ball. So we get a new body, and we can measure its volume. Now we can think about T as a parameter. For every T, we get some number, the volume, and this function from T to this number is a polynomial in T. So you can write it in this way. This is just some normalization for a polynomial. It's a polynomial of degree n. N is the dimension of the space.
I guess the binomial is n choose I.
N choose I, yes, so, yes. And these numbers are called the Quer mass integrals of K. This is the name they chose. And as far as the best translation I was able to find is the mean cross-sectional measure. This is when you take these words and translate to German and stick them together, this is what you get. Okay, so this amazing statement of Steiner relates polynomials and the volumes of bodies. And this is maybe very much related to things Cynthia is thinking about and others. I just see you right now. And now you can ask, what are these numbers that are written here? And then Kubota, which is another person, told us how to compute these numbers. So he said, you want to know what is this number? You take your convex body and then project it to a random I-dimensional space. You measure the volume of the projection, take the expected value, and this is the number. Okay, so this is called Kubota's formula. And for example, you can see here from this formula, if I is n minus 1, this is the surface area. This is Cauchy theorem. If I is 1, this means we project on a line. This is the mean width of the body. the sort of the projection on a line is the width in this direction. So these numbers have geometric interpretations, these numbers that are hidden in this polynomial. Okay, so this is the third story. And what is the problem with, so before the problem. So now Alexandrov proved a list of inequalities with these numbers. In all of these numbers, you can replace K by a Euclidean ball and get a smaller quantity and many more isoperimetric inequalities. So when I is equal to n minus 1, this is the standard isoperimetric inequality. When I is equal to 1, it is called Urysohn's inequality about the mean width of a convex body. And now you have many more of them for I equal 2, 3, and so forth. And now, as before, these numbers are not affine invariant, as we saw before. And now comes the affine square mass integrals. Just replace this number with its nth power, minus nth power. You get a different measurement. And the way they called it is the affine square mass integrals. These are the square mass integrals. And these numbers are affine invariant. So this is the reason for this somewhat unpleasant name.
So, Amir, affine invariant, you mean transformations that are affine and preserve volume, or all of them?
Preserve volume, yes. Volume preserving affine transformation. Yes. Okay, this quantity was defined by Luttwak, I think in a similar way to the way I told the story. Then Greenberg actually proved that they are affine invariant. So it happened, as far as I know, after Luttwak defined it. And Greenberg attributes a key part in this affine invariance to a calculation that Furstenberg and Zucconi did for ellipsoids. So this is the story behind this affine invariance. And this affine invariance is a local statement. So you apply a transformation to K, this sort of, you can translate it to the measure on the Grassmannian. It gives you some number that goes out, and you can see its effect on the projection as well. And these two things cancel. This is the type of calculation you okay, so now instead of these inequalities, we have potential stronger inequalities, and this is Luttwak's conjecture. So Luttwak conjecture is that you have inequalities like Petty's inequality for all of them. And now this quantity is affine invariant, which means that a ball or an ellipsoid give you the same number. So the equality should hold for ellipsoids. Okay, so this is Luttwak's conjecture from somewhere in the 80s.
So this is a stronger conjecture because the phi's are the minimum over all K in the previous, in the W that has, that is a fine transformation of the other body, right? W is,
so W is without the nth power. So W is the 1th moment,
Okay.
The other one is the minus n moment. Okay. So it is okay, so this is Luttwak's conjecture and some comments about it. So this is because of convexity, this is strictly stronger than Alexandrov's inequalities. And for the case n-1, this is Petty's inequality. This is what I explained before. And there are many related research about this, several proofs of this inequality, and some functional corollaries, functional inequalities that follow, not corollaries, but sort of conclusions. The case I equal to 1 is called the Blaschke-Santalot inequality. And this is about the projection on a line. So these two extreme cases were known. And the conjecture is about all the middle between 1 and n-1. Is it sort of clear where, the story? Is it okay?
Yes.
I have some questions, but I don't know if I should interrupt you because I'm a little bit lost. I mean, I'm superficially, I'm understanding, but.
No, you should ask.
Go ahead. Okay. So back to Steiner, where you related, you know, k plus some multiple of the ball to a polynomial. Can you say a little bit about why that's true? And then also the CNIs. Yeah, so I guess a similar question to what Vijay asked before. So it's two questions.
Yeah. So I guess this. If you actually want to know all the details,
I just want to give some intuition about this, about Steiner.
So to prove it is one thing.
No, I'm more.
Yet intuition is a very different thing.
Yeah, intuition is fine.
No, so actually proving is much easier than for me. Okay. You can prove it okay. By induction.
Of course. Okay.
So this is briefly. And also Kubota formula is sort of, you can do induction, a similar sort of, the intuition, why is this thing is a polynomial? I can't give you intuition. I cannot, maybe somebody who is more, I cannot give intuition for this fact. Maybe something that is one example that is sort of related. You can look on this number, think of t as being very small. Okay, so this number minus the volume of k. These two numbers are very close because t is small. Yep. So you can divide by t and get a number. This number is the surface area. Because if you inflate k by a small ball and reduce the volume of k, you get just the boundary of the set. So this is a way to measure the surface area. So you can see a relation between this and the first order thing here. Maybe this is, and now this, you can do more and more derivatives. This is sort of going lower and lower into the lower dimensional things.
Okay, that's actually really helpful. So you did kind of do the base case and the inductor stuff.
Yeah, sort of something. Yeah. Okay. So the thing the result, now this is the main result that I proved with Emmanuel, is that this conjecture is true. all of these inequalities are true. Equality holds for ellipsoids and only for ellipsoids. And in fact, if you look on this quantity and ask if we have a body so that all of its neighborhood is larger, it's a local minima, then this body is an ellipsoid. Okay, so this is sort of a slightly different type of statement. So these are two different statements. This one is, it's stronger than this, and it's like, okay, you understand I think. Do you want to, is it clear? Is it okay?
I think, so this is a kind of reverse or stability theorem, the second one. But is it quantitative?
No, it's very much not quantitative. I will give one hint of how you prove it.
Okay.
You will see something.
So one question regarding earlier. So are the queer mass integrals, so they are not invariant to volume preserving linear transformations, are they?
The usual ones are not, like surface area.
Okay.
Okay. And now I want to explain how we proved it. It will be a high level explanation. So here is the machine. The machine is a very well-known machine. And it's also a natural operation. So the operation is called Steiner's symmetrization. The symmetrization is done like this. We have a convex body in Rn. We choose some direction u. And then we look on the perpendicular to u. Above every line, above every point in this perpendicular, we pass the fiber, sort of a line through this point. And then what do? We take the interval, the part of K on this line, and move it to be symmetric, like this. So this is the operation in direction U. This is called Steiner's symmetrization. This operation can be used to prove the isoperimetric inequality, for example, because it does not increase surface area. In 2 dimensions, this is just, you can calculate it. I think this is the first, how it came to be. In higher dimensions, it's not very complicated, but to me, it's not obvious. So this operation does not increase surface area. This is one property. Another property.
For that, you need to say that it preserves the volume.
Yes. Yeah, I did not even write it because, so it preserves the volume because this is, every fiber preserves its length. So it preserves the volume. A third property is that if you apply this operation again and again and again, you can make any body into a ball in the limit. So this is another property of this operation. And the fourth property is that if this body is convex, then also this body is convex. So it's a very nice operation. Okay, and it's a very well-known operation. Now, what do we actually prove? We prove that if you apply this operation, you only decrease this measurement. This is the stronger theorem because you can do it again and again and again, and eventually you will get to a ball. Okay, so this is a more informative statement. Steiner's symmetrization does not increase this measurement. And in fact, what we show is that if there is equality for all u, then the body must be an ellipsoid. If there is no direction where you can improve, then you must be an ellipsoid. And this is helpful in analyzing the local minima property, this type of idea. Okay, so now I want to try to explain how to prove this in a very high level. So the first thing I want to explain is what is called the rank 1 case. So this is the inequality we want to prove. Steiner symmetrization only decreases this measurement. The two cases when I is equal to 1 or to n minus 1 were known. These are the inequalities that were already known. And the reason or the strategy or one strategy for proving these cases is what the rest of this slide. So let me try to explain. We have a body K in n-dimensional space. Now we want to do a symmetrization. So you start with a body K and you make it into a body, the symmetric version of K. You can think about it as a continuous operation, sort of continuously shifting this body into this body, okay? So now we have not just one body and a jump and another body, we sort of have a smooth way to translate the two. This parameter, the smoothness parameter, you can think about it as a new axis. So this axis is Rn in this picture, and this axis is the symmetrization axis, where we sort of push the body towards its symmetric version. And a key point in proving this is identifying some other body, which I called here L, again in the same n-dimensional space, so that this number is the volume of this body L, or actually the reciprocal of this volume. Okay, so this number is encoded by the volume of L. If you understand the volume of L, you understand this number. Okay, this construction, I will try to explain a little bit about it. Now, how do we understand the symmetrization? The body lives in Rn. Rn is all the lines that are parallel. Yeah, this is sort of Rn. And this body L of K can be defined as follows. There is a convex function on R to the n plus 1. Yeah, Rn plus 1. There is a convex function living in this space, so that this body L is a lower level set of this convex function. So this circle is the level set of this convex function, and all the thing in the middle is its lower level set. So L is, it lives here when the continuous parameter, say it is 1, is some constant that we get to choose. So we put it on height 1, and the body is this body. It is defined by the intersection of this Rn with the lower level set. Okay, so this is the way the construction works. Why is this nice? Because if we take a body, move to its symmetric value, and then continue moving to we get the reflection of the body. So we can sort of, when we go down, we get to the reflection of the body. So this line is the body that corresponds to the reflection of the body with respect to the orthogonal to U. And the volumes of this body and this body of the two L's is the same. It's basically the same body as, or with the minus sign, as you see here. Now, because this body, when you shift it to be, when you go to the other side, you get the same body. What happens when you push K but stop in the middle, not go all the way to the other side? You get sort of this, you get this region in the middle. The body you get is contained in the average of these two sets. This is how the construction works. It's a very high level picture. And the point is the volume of this thing is larger than the average of volumes of these two things. This is called, in this picture, the length is the same. So, but in higher dimension, this is called the Brun-Minkowski, it's a corollary of the Brun-Minkowski inequality. Okay, so this is a very high level sketch of how you prove it for the rank 1 case.
Amir, in
yes.
This proof, was anything used besides convexity of the function phi, maybe phi1 or phi n minus, the convexity and the affine invariance? In this picture, I mean, all you used, I think, is convexity of the functional. I mean, you interpreted it as a volume of a body L sub k, but maybe you can always do that. I mean, I'm just wondering if in this argument anything more was used besides the fact that this phi was convex and that you know, the volume of you know, the body K, the original body K doesn't change in this continuous process.
The construction of L is very specific to this number. I'm not sure how to even interpret this picture very abstractly. It's sort of, this number tells you what is this body. You actually look at this number and it tells you, it gives you hints about what is this body.
So you know examples where, examples where the following is not true, that for any convex function there exists a convex body with this property. So maybe that's what you prove of the other phi's at least.
So I will try to explain the problem and how we solve it. This function is this functional, or this function over convex set that is not, so the set of convex sets is not convex. So there is it's a very simple construction. The details are not complicated, but I want to try to explain the new idea. So I hope the picture was clear in the sense that we get a body that represents the number we care about. And by thinking about symmetrization as a continuous process, we can get a geometric representation of what happens for the symmetral of K. And then comparing the two volumes of L of K and of L of SE of K, you pull it out of convexity. In the way this is, like this exactly is the picture. This is not misleading. Okay, so this is the rank 1 case. And now this was known for a very long time, even before Luttwak's conjecture. But for all other eyes, this was it was not obvious how to implement this strategy. So why is this the case? Why it was not implemented? So the reason is something like this. When I is equal to 1 or to n minus 1, the Grassmannian is basically a sphere or a projective space. But think about the sphere, because either it's the direction of the Grassmannian is a point on the sphere, or the direction is the orthogonal complement of the thing you want to sample. So it's the same. You can think about this space as the sphere. And the sphere lives in Rn in a natural way. So you can actually take this body, this object, and embed it in Rn in a natural way. This is how you construct the body L. In higher rank, when the dimension is not 1 or n minus 1, there is no way to do this. You need two, the Grassmannian is a complicated object. You need two linearly independent vectors, for example, to span a plane. How do you access this concretely? Like, what is the geometry? So this is the problem, that it's really not obvious what is this body L. And if we tried many versions of this, and it's whatever choice you make, it is very hard to put it inside Euclidean space, any Euclidean space, like in a way you can control it. So this was the problem. And the way we solved it is by a construction. And so now there is one very simple difference, but key difference between this construction and the previous construction. This body L, the body that you need to do all of this process, depends on K and I as before, but it also depends on the direction that you perform symmetrization in. So you first choose a direction, and then you choose a body. Before, there was some body that was sort of related, and you could do the whole symmetrization in any way you wish. So this is the main idea. Now the price you need to pay is that the thing you actually care about is not the volume of this body, it is some other measure of this body. So I will try to explain what is this measure, but this is the price you need to pay. It's not the volume, it's some other measure. And for concreteness, this body lives in this space. So maybe I will not explain it. It's not a difficult space, and we call it the projection Rolodex because sort of there is like a book of hyperplanes that defines it. So this name was suggested by Manuel, and I didn't know what Rolodex is until he suggested the name. I'm not sure if you know what, I guess some of you know. Okay, so this is the main thing is this construction. And now I'm out of time and I have two more things to say. I'm not sure how you want to, I'm really, okay. So I will try to do this quickly. One is, I just want to hint about what is this measure. It's not a very abstract measure, it's pretty concrete. So there is somebody in some space, it's not important, and we want to to measure its volume, but in a non-Lebesgue way. What is the idea here? So the idea is a very simple idea. So the observation is, if you choose an I-dimensional subspace in Rn, and you intersect it with the orthogonal complement of U, then you get an I-1 dimensional subspace in the orthogonal complement to U. So this happens almost surely, unless you actually fall inside. But now you can choose F in a different way. You can first choose E, and then choose F condition on this E. Okay, so this is a different way to sample a random I-dimensional subspace. And if you want to do this, to interpret this formally, it is written here as a formula. This is called, there is a very large family of equalities of this type, which is about how do you do this conditioning. This is a non-obvious thing to do. And Blaschke, Pachenskin, I don't know how to say it, formulas tell you exactly how to do this. This is the purpose of these formulas. How do you sample F condition on E? And this specific formula comes from a book of Schneider and Weil. And this is a very, very special case of what is written there. And I think it can take 5 minutes to see that it is a special case of what is written there. So, but this is a formula that captures exactly this intuition. Okay. Okay. So this is the measure. It is written here. Okay, so this is one thing I wanted to say. So just the summary so far is that this inequality is true, and it sort of, it unifies several other inequalities. And the last thing I want to say is about equality cases. How do you prove that something is an ellipsoid? You get a body for which this is equal. How do you prove that it is an ellipsoid? And this is another amazing idea, which is called, called Bruhn's characterization. And Bruhn, I think, did it in 3-dimensional space, and then it was later generalized in many, many works and reproved. And the statement is very, very nice. You have a body, a convex body in Rn. You cut it with a 2-dimensional plane in whatever way you wish. Okay, so whatever way you wish, you cut it with a 2-dimensional plane. If it's an ellipsoid, this thing is an ellipsoid. The 2-dimensional object you get is an ellipsoid. But for the body to be an ellipsoid, you don't need every 2-dimensional thing to be an ellipsoid. You just need every 2-dimensional thing to have a point of symmetry, meaning that with the right choice of origin, the body A is equal to the body minus A. So if you have this property, you must be an ellipsoid. This is amazing, I think. And it's called Bruhn's characterization. And then you need to go into the argument and see how do you find this symmetry. And it took us some time to do this. It's not, at this point in time, we were so invested that it seems sort of not, okay, so this is the way you find ellipsoids, by this characterization, which I find amazing. It's a very nice, very, very nice table. Okay, so this is it. This is all the ideas I wanted to tell you. And actually, if I had time, there was one more idea, but I will not not do it now. So thank you very much for this opportunity, and I'm very happy to see many of you.
Thanks, Amir, for everybody. Questions to Amir?
Yeah, so can you say maybe, I mean, if it's possible, maybe a little about like what this new measure on the body L buys for you that phi of k didn't satisfy?
The main, so there are two things. First, the measure is not the crucial thing, I think. The thing that is crucial is that you can interpret this Grassmannian, which is a sort of a complicated object. In this way, you can sort of first fix an I-1 dimensional subspace. Think about it as fixed. And then the rest is Euclidean space of smaller dimension. So now you have Euclidean space to play with. You can do things in it. So the actual thing is done here in this part where we think about on this as being fixed. So I think this is the main leverage.
So you mean that after you fix E, what you do with the X is similar to what you did in the rank 1 case?
Yes, yes. Mm-hmm.
So L has a part in the dimensions that you fix, and now after that, it will look like in your picture before.
Yes, yeah. There is some more complicated calculation, but the picture is the same. Yes.
More questions? So I have one. I mean, so you prove the family of inequalities in which a certain, functionals that are volume preserving and affine are minimized at balls.
Mm-hmm.
And yes, I guess my question before is that, how general is it? I mean, are there other, or are there counter examples to this very general statement that if you have such a function, when you apply it to a convex body, it's always minimized in a ball?
I'm not sure. So maybe one concrete question is that I don't know the answer to is, instead of Lumi-Sweetney inequality, you can take other inequalities where the coordinate system is important and try to just symmetrize them and see what happens. And I think the ideas here cannot directly translate to this general framework, but maybe there is some mechanism.
It seems like the generality in which you explain the projection Rolodex may suggest that you can apply the same.
Yeah, maybe I did not. Because this is quite general, but this construction, where is this picture? This construction is specific for this. Maybe for other constructions, there is a way to do this, and maybe there is not. I'm not sure. I don't know.
I mean, is there like any like Hadwiger type theorem in this affine queer mass context? Because if there is, then like maybe what Avi's saying is just a corollary of combining those two things.
I don't know.
What you're asking about analog of what?
Yeah, so I think in the usual queer mass integrals, Hadwiger has this theorem that like every rotation invariant and translation invariant function you can define on convex bodies can be written as a linear combination of the queer mass integrals. And I was asking if something is true for the affine version. And if it is, then one can try and prove the statement you're conjecturing by just applying it to the individual queer mass integrals.
Yeah, I don't know. It's a this point, it sounds reasonable to me right now, but I don't see the subtleties.
Yeah.
Good, that's a good way to take a break.
Yes.
When everybody's optimistic. More questions to Amir. All right, thanks again.
Thank you.